thanks to everyone who's come, and as I said, I'm very pleased to welcome not only computer science alumni, but alumni from other faculties who chose to attend, because we live in an interdisciplinary world, and you can't just silo yourself and say this is a computer science chalk. If it has appeal to geosciences or to humanities or any other area, welcome. Also welcome to any students. It was a pleasure lately to get in touch with the presidents and representatives for the computer science undergraduate students and the Graduate Student Society. So they've spread the word out that students are welcome this evening if they are interested. And finally, thanks in advance to our guest speaker, Faramarz Samavati, who it is my pleasure to introduce. Faramarz Samavati is a full professor of the Department of Computer Science at the University of Calgary. He is currently one of the associate heads of graduate director of the department. Faramarz's research interests include computer graphics, virtualization, visualization, 3D imaging, and geometric modeling. Dr. Samavati has published more than 120 papers, 1 book, and has 2 patents. Makes me wonder where my life went. In the past 5 years, he has received 5 Best Paper Awards, Digital Alberta Award, the Great Supervisor Award, and the University of Calgary Peak Award, which honors contribution to the development of new technology and innovation. So with that said, Dr. Samavati. Which do we have to get you your slides up? So before he takes over, I'm going to put this microphone over on the side there, and if anyone wants to ask a question now or at the end, we'll be able to hand it in to the crowd, or you can come around to the mic, whatever's more convenient for you. You have to click there. Just close that.
Okay. Can you hear me? So thank you, Daryl, for the nice introduction. And I would like to welcome to all of you as a member of the University of Calgary. And I recognize some of familiar faces from several years ago. And today my talk is about geometric modeling to digital Earth. This is 2 terms here, which somehow looks not very connected, and I hope I can make a good connection through this presentation. But before starting my presentation, I would like to acknowledge and thank several sponsors: University of Calgary, Pixis Innovation, NSERC, and Grand Network of Center of Excellence for supporting my research. So let me give a little bit of my background and a little bit history here. I arrived at University of Calgary in 2001. So my main research area was geometric modeling as a part of computer graphics. And the main problem which we want to address in geometric modeling is how to create digital content for applications like game, movie, CAD. And if you think about movie industry, you not only want to create objects, you want to later to animate those objects. So you need to have a reasonable modeling technique, which later you can, for example, move the head, move the eye in a different resolution, and techniques like subdivision, multi-resolution, hierarchical modeling are kind of techniques for addressing those kind of challenges. And I have been working on those, and also there are some fundamental challenges in that area, which I ended up with some techniques which we call meta-modeling. And later I realized it's not just a mathematical representation. We need to also have a good interaction with our software. So therefore, I worked a lot on sketch-based modeling. And in the past 16 years, I have been working on visualization, medical imaging, and digital Earth. So though these seems kind of diverse area, but there is a kind of common ground, and I'm going to talk about One of them today is digital Earth and how geometric modeling and computer graphics can contribute to address some of the challenges in this application. But before doing that, because sketch-based modeling is there, and it's good to give a little bit high-level glimpse of what I did in that area. And I would like to demo this GR Sketch. It's a system which we developed. Is based on the PhD thesis of my former student, Luke Olson. The mathematical foundation and also interface of that was presented in a top-tier journal in computer graphics, and we received the best paper award of that journal in 2011, and also we presented this work in Alberta Digital Award ceremony, and we received the best software award for that piece. And let's see what is the point here. So we would like, assume you want to create a 3D object for game. And you know Angry Birds, and dog is a bird, so let's try to create a 3D dog. But you just have a photograph of a dog, and here you see a demo of this system. User draws some lines, some important features, and behind scene, using optimization, a 3D object is just created on fly from that. Now, because dog is bird, you can have angry dog game. So this is a kind of going from very fundamental mathematical work to real application and creating software tool for that. But let's go back to the main kind of goal of this talk, which is digital Earth. And for that, let me first try to state the problem here. So currently, we have many geospatial sensors. For example, Landsat 8 is one of the few hundred satellites orbiting the Earth and capturing high-resolution images from the Earth. Landsat 8 only creates 700 high-resolution images per day, and every 16 days it has it creates an entire picture of the entire Earth, and it goes back and creates another layer in another 16 days. So we know Earth is huge and live, and this is a kind of live capturing the Earth. And this is only one of the geospatial sensors. LiDARs, smartphones, seismic scanners, even now drone imaging techniques. We are just capturing data about the Earth. And we are collecting data about the Earth. So, and we are facing with the challenge, explosion of the volume and variety of geospatial data sets. An important question here is how to integrate this huge, vast amount of data in a holistic and consistent manner in somewhere which we can deliver, visualize, and later make decision about the Earth. And we know we need to do this decision making a lot, and it's important for us as a human being to have a reasonable decision about the Earth. And there is a vision here, something which is called digital Earth. And the term is coming from Al Gore's talk in '99. He used this as a kind of visionary at that year. So we need he was talking about the need for a digital representation for the Earth as a placeholder for keeping all information about the Earth, such that we can, for example, choose any area, small like a hole on a golf course on the surface of the Earth, huge like an atmosphere of North Pole, or big like a reservoir underground. And then all related information about that region can be retrieved, processed, and delivered to decision makers. So that's the vision for digital Earth. So, and for doing that, because everything has a location and spatial, we need somehow a reference model. So for addressing and locating important geospatial entities on the Earth. And it should be global, not for a certain region, not just for Europe, for the entire world. And unfortunately, the conventional techniques, which is based on continuous math, lat-long representation, cannot address many of these challenges and this explosion which is happening. So we have this need for multi-resolution data set. We need to add this live update. We need to have fast transmission. And having lat-long representation is not helpful for doing that. So, but there is a disruptive method, kind of alternative method, which is, as expected, is a discrete representation for the Earth, which is currently called discrete globe grid system, or DGGS. But the core idea is we discretize the entire Earth to the small uniform cells, which are going to be used as a placeholder for collecting and assigning geospatial data sets. These cells, regular cells, should be refinable. It means a bigger cell should be refined to the smaller cell in order to support this multiple resolution, multiple spatial resolution as we need for the digital Earth. And for sure, we need somehow to address these cells, give a unique address to each of these cells as a kind of relationship with the data structure and databases later. So we need somehow indexing technique for these cells. And that's the core idea of DGGS. One simple solution, or the easiest DGGS system, is just use a single 2D domain, as you see here. Then use a big rectangle, divide that to 4 smaller rectangles, and do that iteratively. And then you have this nice hierarchy of regular cells. Then map that to the sphere or ellipsoid as approximation of the Earth, and go from there. So use one single 2D domain for approximating the Earth. But this is going to be a bit problematic for us. It goes back to the map making issues. And this is a screenshot from Google Map. And you see here Greenland, and you see here Brazil. And Greenland looks much bigger than Brazil, but in a sense, that's not true. Greenland is almost 1/3 of Brazil. So, but that's distortion happens because you take sphere to a 2D domain. So this has been the source of misunderstanding of mapping a lot. And it could be dangerous for visual analysis, for example. For example, here you see recent earthquakes in Greenland and earthquakes in Brazil. From just a simple visual analysis, people can say, OK, Greenland is safer. But in a sense, if you have an area preserving mapping, no, that's wrong. In fact, Brazil is safer in respect to the earthquakes. But that's coming from area distortion. And this is a funny video to show whatever we do, we can't do. We can avoid kind of distortion here by using one single 2D domain.
All right, here we go. If I want to turn this globe into a flat map, I'm gonna have to cut it open. In order to get this globe to look anything close to a rectangle lying flat, I've had to cut it in several places. I've had to stretch it so that the countries are starting to look all wonky. And even still, it's almost impossible to get it to lay flat. And that right there is the eternal dilemma of map makers. The surface of a sphere cannot be represented as a plane without some form of distortion.
So, is a kind of potential distortion or aerial, angular, shape, distance, direction, and whatever 2D map you are going to use, some of these will happen. So there is no way to avoid that. But in the context of digital Earth, because cells are going to be placeholder for information, area preserving is important. It's the most important thing, because you want to have these cells to be used later for statistical analysis, for getting integration of somewhere, to do simple statistical analysis. You need to have area preserving. And I'm trying to give a basic idea of one of these area preserving mapping techniques. It's called azimuthal. So for a point on the sphere, you can connect that, and then the intersection with this tangent plane, P prime, is going to be projected points. Now, if you have a ring there, it's going to be mapped to this red ring here. By changing the spacing between, spacing between these circles, you can maintain the area. And that's a trick which is happening mathematically in the azimuthal area preserving. So if distortion is unavoidable, what can we do to at least reduce that? And that comes with the idea of DGGS. You can start with rather than one single 2D domain, you can start with a multiple 2D domain. Let's start from a cube, which is 6 2D domains. And cube can approximate sphere better. And for each of those flat, we can have a less distortion when we go to the curved. And there are many choices to start. And here you see, in this example, we have started from icosahedron. And it's closer to a sphere. When you map it to a sphere, then the distortion is going to be much less than one single 2D plane. And you can have a variety of choices. You can start from cube, octahedron, icosahedron. Even you can start from buckyball or truncated icosahedron. Is much closer to a sphere, and the distortion is going to be much less when you start with that. And there are many DGGS systems which start from one of these polyhedrons. So another aspect of DGGS or grid system is how to refine cells to the smaller cells. So if you start from cube, you can divide each side of the cube to 4 smaller or 9 smaller quads. And this is, again, decision of the system which they want to use. We have seen some DGGS systems start from cube and use 1 to 9 refinement or 1 to 4 refinement, each of which has its own pros and cons. But it should be some way to refine and make more and more cells. That's mandatory to support multi-resolution aspect of digital Earth. And finally, we need some kind of indexing for cells as a unique identifier to address cells and to assign and retrieve data from cells. One general approach to address that or to solve this problem is hierarchical based indexing. The indices of the children's cells is inherited by the index of parent cell by just adding a post or prefix numbers there. And you see, this is called hierarchical based. If you have this kind of indexing, then traversing the hierarchy of cells are going to be very straightforward, very efficient. Alternatively, you can use coordinate-based indexing. You can use a Cartesian coordinate for each side, then use a kind of integer coordinates for that, and based on that, you can go and find the indices of the children and adjacent cells very easily. This is called coordinate-based, and the other approach is something it's called curve-based. In this approach, you run a curve through all cells. The intersection of that curve with the cells provide you a sequential indexing. And techniques like Hilbert space filling curve or Morton space filling curve can be used for traversing all cells. So let's see some of the state-of-the-art DigiGES system. The famous Google Earth is a digital Earth system, and it developed right after Al Gore's talk. So we started with the keyhole and then acquired by Google the technology. Google Earth uses only one single 2D domain and use cells, quad cells. Refinement is 1 to 4, and indexing is coordinate based. So I think I'm okay with all these choices except with the one single 2D domain, because that's going to be very distorted. And in a sense, Google Earth is good for non-professional and is good for if you don't want to do statistical analysis. So just have a sense of what's happening there. Also, it's good for getting direction, because direction is going to be preserved on that. So Pixie's Digital Earth is another digital Earth system. Pixie's, I have been collaborating with them for many years. The HOS is much kind of harder thing to do. They start from truncated icosahedron rather than just one face, 32 faces. They use hexagonal grid. When you have hexagons, hexagons are best shaped when you want to do sampling. They are optimum in sampling. They are much uniform than quads or triangles, but they are very hard creatures to deal with when you want to render or transmit all this rendering engine and work based on triangle rather than hexagons. So that's one challenge which when you work with a hexagon. Pixie software can be downloaded for free from their website. And if you are interested about digital Earth and this DigiGES system, we have a survey paper published in 2015. So we reviewed more than 230 papers in that survey, all kind of related work and state-of-the-art technology related to digital Earth and DigiGES can be found in that paper. So this was a mostly introduction about a good disruptive method for developing a digital Earth system. Now let me talk about what happens in my research. So my research program, in fact, covers 3 streams. One is about DigiGES foundation and extension. The second is mostly I am trying to address this question, how to efficiently process stream massive data at different resolution in internet, and how to visualize in understandable and engaging ways this massive data in the context of digital Earth. And because I knew I have a broad audience today, I selected this stream to present and show some of my research project in that team. But because I have a large team of graduate students, I thought maybe it's good to give a couple of examples of other streams too. For example, in the context of DGGS foundation and extensions. So one of the current challenge between different grid systems is, so you may have a different cell structure, different hierarchy. Now how to interoperate between these? So in time, they are going to collect a lot of data, each of which is associated with that particular grid system. How to communicate and interoperate between these grid systems. And one way to address that, we call that hierarchical grid conversion. So this is the core of this technique which we developed, is some simple, fundamental geometric transformation which can take one grid system, hierarchy of grid system, and provide you another hierarchy of grid system, depending on what you want to do. This work is done by mostly by my former PhD student, Ali Mahdavi. And this is not just about the Earth. It can be used for any kind of 3D meshes. We can use this for remeshing any given 3D mesh, as you see in this pawn example. So in the same spirit about DGGS foundation and extension, so all of these examples which I have provided you so far is about grid system for the surface of the Earth. Now, a good question is, what happens for volumetric solid Earth? And this is a kind of research project which my new master's student, Benjamin Olmer, is working on that. He's sitting there. And here you see some of the recent results of his work. Here, for creating volumetric grid, we need to come up with an Earth-centric grid. We don't want to have a cube of voxels or baby cubes, because that's not going to be Earth-centric. It's just space representation. And we also need to index these cells, and these cells should be uniform in the volume as much as we can. So it's not an easy thing to do, and I think Ben is doing a great job, as you see here, some example of his work. So, and you can increase the resolution, and it's ready for feeding with a volumetric data set, which is the next stage of his work. And as a kind of example of the second stream of my work, how to efficiently process, transmit the data between client server and DGGS systems. Currently, my PhD student, Troy Allerson, sitting somewhere, yeah, sitting there, is working on this problem. As we knew from many years ago, wavelet transform and this kind of techniques can be was very successful in image processing, image compression, video compression, and we were interested to explore multi-resolution wavelet techniques for doing the same thing for data, geospatial data sets. However, Earth is not flat. The surface of the Earth is not Euclidean space. Therefore, many of those techniques need some kind of projection. And as soon as you have projection, you end up with a distortion again. So the question was, can we do wavelet transform, for example, on the surface of the Earth rather than leaving that non-Euclidean space to the plane? And that's something which we recently did with Troy. And we called multi-resolution on spherical curves. Here you see one spherical curve is the outline of Mexico. And this is a high resolution vector data, but it's a spherical curve. With our technique, you can take it and make it coarser and get some wavelet details and now use compression or transmit that or solve some problem and then come back to a high resolution. We published this last year in Graphics Journal Graphical Model. So these are some example on other stream. There are many other works which is going back to the core mathematical fundamental aspects of the digital earth. But today I am mostly would like to describe some of the visualization project in my team. And the first one is the work of my former master student, Mark Sherlock. He's around yet. So this is about interactive data styling in view-aware digital earth. And rather than I talk, I think Mark is going to talk.
In this video, I'll be demonstrating our work for interactive data styling and multifocal visualization for a view-aware digital earth. Our globe works with a variety of datasets. These data are indexed by a discrete global grid system and are converted by a server on the fly to the textures and geometry that are requested by the client application. We use these textures in a way that produces a variety of visualization choices. This globe is currently using a texture just as RGB values. A dataset containing coastlines and elevation can be added to this, and when mapped to parameters such as glossiness and normal perturbation, it can add a great deal of depth to the result. We can also add other data in unconventional ways, such as etching political boundaries into the globe, or causing datasets to stand out. In this case, world population density is caused to extrude and become emissive. Since the choice of how these datasets are mapped is made on the client, the system can style datasets without the need to acquire new data from the server. In this scenario, we can blend between different stylings of the same 4 textures present on the client. These data may be combined, blended, or filtered in a multitude of ways. Datasets may also interact on the client. This is a visualization of mean surface temperature in 2015. Switching to a dataset of projected mean surface temperature for 2050, the alteration is difficult to perceive. However, if we simply subtract one dataset from the other through a minor change in styling, the difference becomes far more apparent. In addition to improved styling choices, our globe is also capable of fast visibility checks, allowing for applications such as multi-level focus plus context visualization. Multi-level focus plus context visualization on the globe allows multiple views of the globe to be available to the user at the same time, while maintaining awareness of scale and location. These views present a scale hierarchy and can be interacted with to provide an alternative method of exploration. This multi-level focus plus context visualization is also compatible with our data styling techniques, even allowing for purview styling.
So what's the methodology behind of this? Very technical, just to have one slide to explain. So we have a client server setup in DigiJS setup, as you see in this diagram. So the server is here is a Pixis hexagonal grid system with a lot of data sets which they have already gathered for about the Earth. So on the client side, we have very simple DigiJS system. It's a quad-based, something which we can do simple rendering on that. And there is a transmission happening, and for doing that, we have to convert the grid, hexagonal grid, to the simple quad rhombus kind of grid, which we use that technique which I mentioned about hierarchical grid conversion. And also we use, we encode data to the layers of this and submit those texture layers to the client. Now you can blend those texture layers using resources of the client graphics hardware of the client rather than on the server, which is going to be heavy on the server side. And that's the core idea behind of this technique. There are, for sure, a lot of technical details. But after even you saw this cool video of interacting in the virtual world, rotating there, seeing those things, there is still a missing aspect of this virtual globes, and is the lack of sense of touch and having a better, tangible kind of visualization rather than just virtual. And there is also a fundamental dilemma in this 3D interaction is 3D viewing. Always there are some flaw in a 3D viewing. Some parts are hidden, and when you interact, the interaction should be natural, and that also makes things complicated. And when you also have multiple data sets, it's going to be even more complex. And to address these things, one potential solution which we think is cool to explore is using physically visualization of geospatial data sets. This is something which is explored by my PhD student Hessam Jawahirpur and also former PhD student Ali Mahdavi. So we try to use 3D printing to create physical visualization. And how exactly we do that? First of all, you see here there is a panel. This panel is exactly represent a piece of the Earth. And you can assign various data sets on that, take those out, and work with that in a more tangible way. Work with the geospatial data sets. Here you see how we are doing that. So again, we start with the Pix's hexagonal grid system. But because we want to really print these things, we convert those to the rhombuses. One of these rhombuses is a 10% of the board. So in fact, in this figure, we have 10 of these rhombuses. And each of those is divided to 9 smaller rhombus, and one of them is highlighted here. We use the geometry of that. These are 3D mesh. We use geometry of that and export that to the printing software for printing this piece of Earth as a panel for holding various data sets associated to that panel. And this is a really one 10% of the board you see here. And here, as you see, this is associated with the Western Canada region. And one question was how to evaluate such a system. And for that, we are collaborating with a famous world expert of the geographical education system, is Lynn Merman, and she is an associate prof at the University of Montreal. And she had a sabbatical in Brisbane, Australia, a few months ago. She took our piece and took it to a school in Australia and asked a student to do some task based on that. So one of the issues which you may know now is flat Earth versus the curved Earth. At least here, they see the curvature of the Earth. That is important. And when they switch one data set to another data set and they find the corresponding places on that, it also helps them to have a better understanding of the data sets. And her initial feedback seems students love that and work around that, and they had a lot of fun. And she's going to do another study at several schools in Calgary soon. And this piece, and also the other piece which you saw, you can find on the desk outside of this room. If you want to go and check them after the talk, feel free. And also Hessam is here. You can talk to him about aspects of this work. But as soon as we did that, it was an important question: how to support dynamic data sets. So when you have this layer and replace with another layer, you are working with static data sets which have been fixed and set before. And this was an interesting question, and the answer and solution which we came up with was to use a curved display, a multi-projector setup, a kind of installation, using, again, DigiGS as a source. Because the good thing about DigiGS is we can divide there to the smaller pieces, and we know what happens for each of these pieces. We have the data set associated with those pieces, and those issues have already been solved. So this is the main concept behind of this project, and this is a work done by my master student Shima Davkha and Kathy Etemad, postdoc, and my former PhD student John Burrows. He's a coordinator of visualization research at Taylor Digital Library. So what's happening in this project? So again, we start from this 1/3 of the word pieces. We print those as a kind of panel, display panel. We cover those with a paper material which can be used for projecting. Using just regular projector is a kind of a screen for projecting things. Because we want to use multiple of these panels, it was some snaps and to attach these things. All these things, pieces have been printed using 3D printer. In our lab, we have a very small, affordable 3D printer. Is a Maker Gear M2 model. Is not a very fancy printer, but I think the technique is sophisticated to take advantage of that printer for doing these things. Here you see the setup which is happening in behind scene. So we can use one or multiple panels per projector. And with a multiple projector, we can fit several of these panels. I think in a final installation, we need 5 projectors, for each of which 2 of these panels can be fed. And then we can cover the entire Earth. So that's, we haven't done that, but so far we have implemented curved display with the 4 of these panels. We got the acceptance from a visualization conference last month, and Shima is going to present that in January, this work in that conference. Here you see a live video of this. In a sense, this is off-the-shelf installation, very economic, cheap installation of such a curved display. There is a similar project in a spherical projection. They use a very expensive installation, and they don't use area preserving. Still, you have those kind of misunderstanding when you use that. You may have seen some of these in museums here and there, but this is very kind of economic installation. And I think there is this installation you can find again on that desk. You can go and look at that after the talk. So another problem with the current digital Earth system, including Google Earth, is rendering. As a computer graphics expert, I don't like this kind of rendering. This is a view of Yellowstone National Park. So mountains, valleys, lakes are not that apparent and not vivid there. If you look at the same place in this wonderful painting of Heinrich Baron, so it's a very live, vivid painting. You see all of those features, and it's very engaging. You like to look at that and explore that region rather than that boring Google Earth. And a few years ago, I was thinking, what if we create such a result in the Google and the digital Earth? And for doing that, my former master student, Alex Braun, followed that vision which I had, and we end up with something which we call real-time panorama maps for digital Earth. It's a software which gets these simple data sets available and creates similar effect with Heinrich Baron's painting, and it does it in a kind of fly-through, live, not just one single image. And for doing that, we had to go and analyze Baron's painting. Fortunately, there is a website dedicated to Heinrich Baron, and for more than 500 of his painting is there, and we analyzed those and came up with several things. And one of the important aspects, which I can at least tell that aspect here, is if you look at the far region in this painting, it looks like horizontal to your view. If you look at the close by, it seems vertical to your view. So in fact, the scene has been bended. And so therefore, it should be some kind of space distortion to show that effect. Also, we had to mimic his painting colors, trees, water, atmosphere style. And here we go, the same result of our system for the same region, Yellowstone National Park. We presented this work in ACM Expressive 2017, and we received Best Paper Award for non-photorealistic rendering paper. And to see this in a kind of live demo, so it's not just single image. You can fly through of the region. Now imagine this could be added to any digital Earth system, including Google Earth, then you can have those kind of images. So I was talking about having this explosion of the data set related to the Earth. But unfortunately, most of this data set is satellite images, flat 2D vector data set. OpenStreetMaps, you have a lot of data, but it's talking about vector data, nothing really 3D. Some very few places, fancy places across the world have some 3D content already there. And one question for us was whether we should wait for the technology to come up with a 3D content, capture all 3D content of the world, or whether we should come up with a tool, software tool to do that. And because I have been working on the 3D modeling for a long time, that was another project which we wanted to do. We wanted to augment geospatial data set using interactive modeling tool. And that's the MSc thesis of my former student, Kaveh Ketabchi. He's now in Google, and former PhD student, Adam Runions. We presented this work in Cyberboard, IEEE Cyberboard 2015, and received, again, Best Paper Award of that. And let me show the video and explain important aspect on this when the video is running. So this is a Glenmore Dam. You have two sets of data available in digital Earth, so elevation data and aerial photo, orthophoto. If you add these two pictures, you receive this kind of fake 3D, but it's not really 3D. It's because these two data sets do not match nicely. Here, the river, I think it's the Elbow River, it goes up. And so therefore, we came up with a terrain editing tool. So it's a sketch-based tool. So whenever you feel something strange is happening, you draw that line, then you correct to a straight line. And behind scene, as soon as you do this correcting with the strokes, an optimization model is solved to modify the underlying terrain to respect these strokes and this sketch provided by user. And as you see, the entrance of the river to the dam is bended with just one line. We can correct that. And also here you see we are creating the basin of the dam, and this pathway is bended strangely. We draw a stroke and then correct that. Now it looks better. So this is a modified digital elevation model. Behind scene, the underlying mesh has been optimized to respect that. But we have also a good opportunity to add water bodies. For example, here we are creating a separate object as a water for dam, lake of dam. And the same thing can happen for river. Now we have two water bodies here. Rather than just texture, we have really 3D object. We can use these objects for simulation, flood simulation, or any kind of other more advanced graphics things. For vegetation also, here you see a lot of trees, but those are just texture. Nothing really 3D is there. But as soon as you use this blue stroke, the system creates 3D vegetation respecting the vegetation of that region and also the rendering of coming from the pictures. These are really 3D vegetation. And we also had fun to create 3D structure like buildings. We created this interesting tool to steal any 3D building here from downtown Toronto. It canceled the perspective issues. And now you can use that 3D building, which is has also texture of that, and put it in that Glenmore Dam region. So we have a high-rise building from downtown Toronto and the Glenmore Dam. Here you see some more results. We had some fun for campus, University of Calgary. This is the math science. My office somewhere is there. And we have this fake lake there. By just some few interaction, we have created this interesting result. But as soon as I saw that result, I was so eager to create a 3D print of that result. So the scale here is very different from the scale which we had for physical visualization. In physical visualization, we are talking about 10% of the world is going to be printed. Here we are talking about a tiny piece of the world, but with a lot of details and a lot of 3D details. And this is a work which we are doing with a current MSc student Kamyar, and with the help of Hessam and Ali again. And for doing that, we selected this famous landmark, Lutterbrunnen from Bern in Switzerland. So we selected because this landmark has a lot of details, and also the data which we needed, it was there. And you see a lot of vegetation region, very interesting elevation data sets, many buildings, rivers, and other features. This is a Google Earth view of the same village from this view and the other view. And we were interested to 3D print this region. And here we go, the result. And you can find this piece outside on that desk too. But it is interesting to know the entire thing has been printed by this small Maker Gear 3D printer. And the question is how this has happened. So this is a closer view of the same view, landscape. And this is a collaged view of the real 3D printed landscape on Google Earth, so it fits nicely. This is a closer view of the jungle, the vegetation region. And as you see, something is happening here. So if you ask architects to create this kind of vegetation or this kind of elevation, it's really, really hard. But we can take advantage of 3D printer and we can have this kind of nice result. How exactly we did that? There is a very sophisticated software system is doing this for us. And in this software, we take vector data, for example, boundary of a jungle or lake or river, roads, and elevation data. These two sets of data available freely for most of the world. We create a 3D mesh from those with respect to the features. So this is all, there is again an optimization problem has to be solved here. And then we, for each of these features, for example, for the lake or jungle, we have to create a submesh, separate submesh, because we are going to use a different layer. We're more likely to use a different color for that. For example, for jungle, we are going to use a green material. Our printer has only one head and can print one color at a time, but you can change the colors if in the next printing session. So, and here you see the several layers for each of these features, but because we are going to attach those layers to underlying piece, we need to anticipate their kind of existence. Therefore, we need to offset underlying mesh for doing that. But unfortunately, the entire thing cannot be printed by one, but with this small printer, and more likely with the even larger printers, still we need to segment that to the smaller pieces. And this is a mesh segmentation which we need to do. And therefore, software takes this and in the end of the day makes a lot of pieces for us with some guiding how to assemble those pieces. And the final physical model can be created through a manual process by attaching these pieces together. That's the thing which is happening. I think the time is up, and some of you are tired. So there are some other visualization project in my team. I think there is a project, ongoing project for improving visualization of map entities, like labeling of maps. Cathy is working on that. Also, there is another project on dynamic, how to visualize dynamic data sets, time-varying data sets, including Landsat data set, and Gurav is working on that. But these are ongoing works, and hopefully we will have some achievement soon. And it has been a great opportunity for me the past few years to explore this journey of using graphics, geometric modeling for solving digital layer challenges. So I have been lucky to work with a great group of graduate student researchers. And there are a lot of unexplored future work and ideas which we are going to explore. And here you see a nice volumetric grid, empty of data, waiting for some data to be fed. And if you have a real problem, want to collaborate with us, feel free to Google my name, send me a note if you are interested to do that. Thank you.
Thank you so much. I understand if you have to rush off because maybe you only paid for parking for an hour or something, but I would love to open the floor to questions. Dr. Samavati, do you have a few minutes to stay if there's any? Excellent. So, open mic. Anybody? Yes, please. I'm going to hand you this so that you're on the video.
Thank you very much. You mentioned that there are problems with current 3D visualizations. You're familiar that in the library here, the Taylor Family Digital Library, there is actually a podium with a glass sphere on it, and it's a 3D screen. What are some of the issues you see with that kind of representation versus this segmented representation that we have an example of outside? Because to the uneducated eye, the spherical screen seems like an easy solution, but clearly you, as an expert, see many issues with it. So I'm curious as to what those are.
I think the main issue to me is area preserving. And if you use simple spherical mapping, not only you don't have area preserving, you have other kind of distortion. And many of these projectional spheres do not have kind of a very accurate mapping. So that's a, I don't know which kind of software is used there, but for example, you can explore whether what's the shortest path between 2 points, whether area of Greenland is this, kept unchanged. So, and one positive aspect in our approach is it's scalable. You can have it pieces. You have even compare Canada with China in 2 different panels, put 2 different projectors. When you have everything on gathered on that, you need to walk around to see the other side, and sometimes it's hard to see that. But you have also option to assemble everything to one single kind of piece if it's interesting. And so this kind of scalability and also disjoint projection and also area preserving are positive aspect. Maybe that system also have some good projection mapping. I don't know that particular system.
So it's not the sphere itself, it's the data going into this. Thank you.
You're welcome.
Yes.
The question that I have, it's very interesting to see the work that you have done over years. One question that I have is, if you have a real 3D objects with unknown curvatures, shapes, and you have some data for that, and you generate an output from the methods that you have used, the question that comes into mind is there any way that you can do error analysis to see what is the difference between the real object versus what you have generated? Have you done any work to just come up with some statistical analysis to identify the key differences?
So for this digital art, we haven't done that, but I am familiar with the techniques, which is, in a sense, is a 3D registration when one of the objects is real 3D, physical 3D. The other one is a virtual 3D. And how to compare that, there are some techniques which is called registration, and comes back from CAD industry from many years ago. There are some papers. So, and I was examiner of PhD thesis in a Department of Manufacturing of the University of Calgary, and the thesis was how to do this registration for getting whether my 3D reconstruction fit well with my original object, and what is the error. So there are kind of well-known techniques for doing that. In general, computer-aided design, and AutoCAD is just one software for doing that.
Hello. Looking at the slide over there, there's a very nice volumetric, how do you call it, a container for data to go in. But unlike the satellites that goes around the Earth, there's not a lot of data that's surrounding the air in certain elevation, things like that. So I was wondering where you are planning to get all those data, or where you're going to find them.
Well, that's a good question. That was one of my reasons to ask this this audience. Maybe they have a data. I know for weather data sets are attached to the space, not to the surface. Also, there are some physics data sets which are coming from space. It's also on the space. And for under the ground, so there are a lot of reservoir data sets. It's mostly on the lithosphere region. So, and I know that's a fundamental challenge for reservoir engineers to integrate whatever is under the ground with whatever we see on the surface. But this is a very new, so we are exploring this for some real case studies. And I hope we can find some data set. Ben, did you find any interesting data sets?
Not yet, still working on that.
Anyone else? Well, before I let you go, Dr. Samavati, I just have a little gift here to thank you for your time putting this presentation together, and also for rounding up all of the grad students and PhD candidates, bringing us lovely displays to put some tactile feel and visualization to the real world of the digital presentation this evening.
Thank you very much.
Thank you.
So. I also would like to thank you for organizing this, particularly Leon, for doing this hard job of organizing this gathering and this presentation.
So thank you. I'm going to put the one slide that has all of the Twitter and the Facebook and the LinkedIn groups back up on the screen here in a second. We are having our planning meeting for our winter semester event sometime in the next few weeks before Christmas. We'll be planning, and then having whatever our talk for the new year will be, probably in February. So keep an eye out for the alumni invitation. And as I said earlier, we're always looking for assistance, whether you have a few minutes to volunteer at the beginning of an event to help hand out the name tags, or if you'd like to come to a meeting and maybe get involved in some other way, find out what other things you could contribute. We're always looking for additional computer science alumni to join the team. And with that, I would just give a shout out to my team. They are mostly here. At the very back, my Vice President, Jack Shan, the Secretary, seated over here, Katie Yoon, Mustafa, our Communications and Webmaster on the videography this evening. I know I saw Mark Lane here somewhere. Did he sneak out? There you are. And I can't remember, did anybody see Eric tonight? Eric is our social media director, so he's probably tweeting away somewhere. So thank you very much for coming.